So thank you for introduction and also organizers for giving this opportunity. So this talk is based on a joint work with Somnath Jha and Ravi Teja Bangla. Both are here present in audience. So this is basically a report on some computations we have done in this direction on Rankin-selberg L functions of or p-adic L values of Rankin-selberg for two eigenforms. So plan is that we'll begin with some preliminaries and then go on to basically first set some notations, and then using that we'll define Selmer groups associated to Rankin-selberg of two modular forms, and then look at the p-adic L values. And finally, in some special cases, we'll give some relationship between them. So to begin with, let us take a modular form F. We take weight K, gamma naught N. So NF is, let's say, the conductor of F, and we take an even type eta, and then we take another form. So this L, this we take gamma naught I. We take given type psi. We assume both are primitive forms. So F and G primitive. Fix a prime P. For simplicity, we actually let us assume that P is greater than or equal to 5, although most of the result which I'm going to state will actually hold for even for P equal to 3, but not for P equal to 2, that we haven't even looked at. So, and also some extra simplification assumptions. So let P doesn't divide NF. So we call it a good prime for F. And so then one more, that both F and G are the ordinary. Okay, so because F and G are eigenforms, so there is a associated to F, and there is a Galois representation also associated to, or maybe let me just use this notation H here, because it's H here. So, and then associated to this also we have Galois representation which we denote by VH, and inside that we can choose a Galois invariant lattice. Of course, this is well defined only up to a scalar multiplication if and it's uniquely determined if the residual representation of this VF and VH are irreducible. Otherwise, it may not be uniquely determined even up to an isomorphism. We take it inside H, and we denote. So because we are assuming this F and H are ordinary, so there will be a filtration in this. VF plus, and then VF, VH plus VH, such that VF mod VF plus is unramified, one-dimensional unramified, and VF mod VH plus is also unramified. So these two are given with the assumption. So now, once I have this filtration, we also have a filtration on tensor product. So this is VF plus, tensor VH plus, and then this is inside VF plus tensor VH. Then we have VF plus tensor VH plus VH plus tensor VF, and then this is inside VF tensor VH. So we'll use this filtration to define Selmer groups of this associated with this representation. there are several possibilities, but for us, we'll stick to the middle one. So we'll use a quotient using this. So we'll use this quotient to define the Selmer group. Although other, if you use other quotients, they are also interesting in their own right. However, in this talk, we'll not discuss them. This is what we'll use to define our Selmer group. But before that, let us look also fix some more notation. So we use A to denote this VF. So let me just call this one V and use T to denote VH. Then E, and then we have cyclotomic character Galois group of Q infinity over Q star. Then for any J, we have for any J, we'll take L minus 1 to Q minus 2. For any J, we define Vj, V tensor to the power minus J, and similarly we have A of J to be A tensor I of minus J. So let put Aj plus equal to image of V. Let me call this one V plus. This one is V, so I call this V plus. Then image of Vj inside image of this in Aj. We have this map from V to Vj to Aj. So via this map, I take this image. So the Selmer group of we are interested in. So I take any field Qn, and let me just first use Aj and then Qn. So what is Qn? So I have two cyclotomic, and then they have this. This is Galois group is denoted by gamma, isomorphic to Zp. And in this, we have tower of extensions Qn with Galois group of order p to the power n. This I denote by gamma n. So Selmer group of this usually denoted by Greenberg-Selmer. Defined as kernel of H1 to sigma to Aj to product of L belong to, or maybe V dividing L belong to sigma and L not equal to P.
Can I ask you the condition on J, this inequality?
Yes.
Does it correspond to critical condition?
Yes, yes. So
okay, so that's what exactly you want to say. Okay, thank you.
So, L unramified. And here we put Aj. This is away from P, and then you also have prime dividing P. So here we have this is H1 and will be unramified, and then here we take Aj mod Aj plus, also denoted by, so this sometime I will write Aj minus to denote this group, this Galois module. So this is what we are interested in, this group. That's the definition of Selmer group which we want to study in this talk. So now we can put this, so take Greenberg over and the restriction map, these are defined. And let us denote xj to use xj to denote the Pontryagin dual of this is Pontryagin dual, that is set of all homomorphisms from this to we'll have QP mod GP. We'll take all continuous homomorphism. So then all the expected things should hold. So conjecture, I think in this form due to Greenberg. First of all, xj is a finite. So xj is a finitely generated. Xj is a finitely generated lambda module. Sorry, lambda module, where lambda is equal to it's Iwasawa algebra over gamma. I have not defined what is OK. So here k is nothing but we take all the coefficients. We have this all the Fourier coefficients of f and Fourier coefficient of h, and then you have values of this was an even type of f. This was an even type of h. Attach all this, you get a finite extension of QP, and inside that you have OK, which is the ring of integer, and inside this also we have pi OK, which is the maximal ideal of OK, which we'll use again several times. This is a finitely generated lambda module. However, the even much more should hold. So this is a torsion lambda module. Okay. Yeah. This is the expectation, and in some, what more can we say about structure of a group of, or rather I should say structure of xj as lambda module. So some standard property which holds for Selmer groups defined using this kind of formula also holds here. So, Selmer group of, so this is sometime I'll just drop this notation GR. Finite kernel and co-kernel bonded by bonded with respect to n. This is the first property, which anyway proof is standard. The way we do it for modular forms or even for elliptic curve, proof is similar. That's one more thing. So let us recall, let us denote by rho f bar to denote the residual representation of f at pi, and similarly rho h bar we denote the residual representation of h. Then if so case A, so these are corresponding residual representations. So then suppose rho f irreducible and rho f bar is not isomorphic to the dual of rho h bar. I suppose this hold, or rho f bar is reducible and rho h bar is irreducible. Then Xc has no finite lambda submodule, also called pseudo-null submodule. So this is again, the proof is essentially there is a much more general theorem by Tom Weston. We just need to so he has proved his theorem under certain conditions. So we just need to check that if one of these two hold, then his conditions are also satisfied. And then so it just means that, so for example, if so this implies, for example, if the Iwasawa, the mu invariant of as a lambda module, mu invariant of xj is 0, then this is nothing but xj is just isomorphic to so finitely many copies of zp to the power some r. This is of course under this assumption that x is a torsion lambda module, and yes, so we want to look at a special case when we can at least say that at least this or this kind of theorem holds. Basically, an example at least where we can directly do this. So a special case, or maybe I'll often refer it as a baby case. Sorry. Yes, so there are results by Lee, Lofgers, and Jervis, where they have shown the Selmer group over Q itself is finite, and then control theorem will give us that. That is what they have done, right? That. Oh, okay. So they can find some twists of that. Okay. So yeah. So under some conditions, it's actually known that. So they have some 11, 12 set of conditions which all of them I don't remember, but then they have shown that this is actually torsion. So there are of course cases where it is known, and we also want to look at some cases here, a slightly different kind of situation. So what is that? So let us look at this situation where we can relate this 4-dimensional representation to certain 2-dimensional representation, so that rho h semi-simplification bar is, let's say, isomorphic to some direct sum of characters. So basically, the residual representation of h is reducible. So in that case, okay, I have to go maybe that side. Yes, that's reducible. That's a different, this condition B is not, so this is not true. I'm not looking at, in fact, I will not look at this condition ever in this. Mostly I'll be looking at when this is irreducible, F, residual representation of F is irreducible. Okay, so yeah.
Hello. Yeah, so in the theorem, this A implies that XA has no finite submodule.
This one here?
Yes.
Yes, if either of these hold, then this is true.
Okay.
So then okay, so Okay, so I think these notations are standard, so I'll just remove it now. Yeah. So in that case, what can we say? So let us assume some more conditions. So suppose I'll state it as a proposition. I'll refer it sometimes, so I'll state it for proposition 1. Suppose, so recall psi was the given type of H, so as order prime to P. Okay, and so this is the first one. And the second one is, so we look at the Selmer group of, so just like we defined for tensor product, we can also look at Selmer group of F. I'll just denote it by F tensor Xi1 over Q cyclotomic pi. So that by this I mean the pi torsion subgroup of the Selmer group. And so this is for both Fi. Right, for I equal to 1, 2. This just means that the mu invariant of Iwasawa mu invariant of this Selmer group is 0 over cyclotomic extension. Second condition, and this is the third one, I need that rho F bar is irreducible. Okay, so in this, if this holds, then we have 0. Everywhere there is a J which I am missing. Maybe I can. J. So in general, rho H bar may not be semi-simple, so we don't actually get this splitting, but we still at least have exact sequence. So as a consequence, of course, this assumption hold, then this implies that then this is exact, and this implies that Selmer AJ cyclotomic dual, which is XJ actually, is isomorphic to some ZP to the power R. So in particular, torsion and mu invariant is 0. Of course, this irreducible and rho H irreducible and rho H bar semi simple is isomorphic to. This implies that this is not dual to this, and irreducible implies that this has no pseudo-normal submodule, no non-trivial pseudo-normal submodule. As a consequence, of course, because this has mu invariant 0, this has mu invariant 0, this also will have mu invariant 0. So we have this. So this special case I have stated because this is, we'll need this again later on when we look at the special values. Okay, so now. So before I move to special values, let me just, okay, so there is one more small correction I have to make here. So we don't really, actually the statement will be true, but this statement will be true, but here we need to remove certain Euler factors, which I'll describe later on. There are certain problematic primes which we need to get rid of, this I'll define. But before I define that and also look at the special values, let me, so this is outside bracket P. So let me just directly relate it with the Selmer group of residual representation. So we have Just note that we have H1 sigma cyclotomic, and then instead of outside, we can look this Galois cohomology group, and we have a map. Outside, and inside this we have Selmer, Greenberg, AJ. So we can basically pull back this here and define a Selmer group of J phi. Inside this, so we call it the Selmer group of residual representation of AJ. And then if, note, so if Remark, if bar is invisible and bar is not isomorphic to OH bar dual, then we actually have both these groups are, so this is an isomorphism, because this map will be an isomorphism. So this one isomorphic to AJ. Yes, so although the way it's defined notation, I have denoted it looks like this just depend on this residual representation, but that is not the case in general because of the way local conditions are defined. Okay, so this is about Selmer group side. Now, let me just move ahead with the section on p-adic values. Here, recall. So the corresponding L function, complex L function is defined as. So we have product of L comma. Let me just use the notations. So this is A plus L minus J yes minus 2 y here and comma and 1, and the remaining thing is sorry, this is sum. And from 1 to infinity, N to the power minus S. So then this is a theorem. Simura that d of L plus M I2 of I of maybe K plus, excuse me, there are some of the powers off, but this is the Peterson unit product. This belongs to Q bar for all 0 less than M then k minus f. So we are interested in some p-adic properties of these value, and actually want to relate it in the Selmer group in some special cases. Okay. Yes. Okay. So this is for any form, so any eigenform, but for us, our special case, yeah, I'm little getting confused right from the beginning. So it's H, and yeah, that much. Anywhere else also, here also. H. Then I should write here actually NF. And maybe I can just use the notation A. H. Okay. Yeah, thank you. Okay, so let's just let me recall a theorem by Hida. So before this theorem, let me fix some notation. So I use this, let XP denote this inclusion from ZP star to UP star, which in fact, I'll view as a map from ZP star to UP bar. And also recall we have a set of measures on X. For us, X will be ZP star. So maybe ZP star, and this OK valued I take. Of course, this is by definition. And also this is bijection. This is a bijection with this. Okay. Yeah, so let us fix this. So then although this is a theorem by Hida, in a much more general case, we'll be stating rather a special case or also a simplified version. And in this form, it is actually, you can find it in an article by Buganis. There exists a measure which you denote by F. I'll write instead of F, I'll write F naught. So F naught is the P stabilization of F at P, and then this is H, and such that for each finite order character I belong to, so I see it inside set of locally constant functions and ZP star with values in UP bar. So again, character, by that I mean there's a map from ZP star to QP star, and then we compose it like this. So finite order characters. Then we have for each mu of naught times H evaluated at x to the power xp to the power j. Xp is that function, and xp to the power j, and then the I. This is equal to, so the entire value is a bit complicated, but let me just write CF, and there is a scalar t which we will not bother about. Then some powers of p. I've not defined what is beta, but let me just write here first. And then e to the power J there is a Fourier coefficient here, P f naught 1 minus beta, and this times d of L plus J. So here that bound for J is slightly different, I'll state. Then H, we apply phi on this, and then we apply tau, the linear operator on this. I naught is the prime to p part of I. Recall I was the conductor of the level for H, and then p to the power beta. This by period. So what is that period? So this is 2I to the power k plus L plus 2j, and then pi to the power L plus 2j plus 1, and then here the other transcendental part, this is f naught. You apply rho, that is the complex conjugation, and then this is weight k, and then you take the linear operator, p to the power it's in this case just np, and here we are taking that the Petersonian product, giving them as a level np form. So this is the interpolation formula of this measure, given by defined by Hida, and then in fact via this correspondence with measures and power series, we can in fact twist it, define it like this. I denote the corresponding power series by this so Pj f times not x to the power xp to the power j minus L plus 1, then multiplied. It's like some twisting is happening, although let us not bother about that now. We want to so compare. So let us state. Again, in this form, I guess this is by Greenberg, although various other people also. So what is this conjecture says? It says that L, so the ideal LPJ, the fact that it's integral measure, it's actually lands, it sits here. Already integral, the way it is defined, and then this is equal to characteristic ideal of as a lambda module, so characteristic ideal of xj, of course, an ideal in lambda. So I can call it also our main conjecture for answer H. Okay, so but a weaker version would be mod b mod 5 or okay. This should maybe I'll start here. Okay. A weaker version would be if once you know it's in their integral, then you can in fact ask, I think that was the notation. This is congruent to mod phi in lambda. Okay, so of course, this is interesting only when the mean variant itself is 0. In that case, I mean, we are interested particularly in this because, of course, there are results by several people. For example, it's by Jinwan. And also, I just have, I mean, again, Leflert's, Jarvis, Lee, and then there is again same authors, but also King, and many more people. Some of our authors will cut. More about on this p-adic Rankin-selberg L functions and also relating it with characteristic ideals. So some of the results are of this kind, where one proves that either L E J divides lambda xj, or for example, by Jinwan you find this kind of result, and also there are some by in these other authors you have, although their conditions are, I mean, they are not common, so cannot combine the results, but characteristic ideal of divides. Also some p-adic function, for example, in both these cases are slightly different, but here in the Jinwan's article, actually it's compared, and he has compared it with Hida's p-adic function in some cases. But however, there are results of this kind. So in this setting, for us, it becomes interesting for us. Of course, once we know that mean variant is 0 and one of these results hold, then corollary will be that actually these two are equal. That is our one of the motivation for looking at these. So let us now come back to that our baby case, where in a special case where we can say something mod p. This again a special case. In this case, of course, we would expect that because we have already related Selmer group for Rankin-selberg of H with F with the Selmer group of, I mean, F itself with J1, J2. So then we should have something similar for these L values also. So then, so how do we go about doing it? So what we do to relate to prove a similar kind of result, what we did for Selmer group for these measures, what we do is the first, so step 1 is lift J1 and J2 to characteristic 0. So J1 bar, J2 bar to characteristic 0, call it J1 and J2. Of course, we do it in a certain way that prime to p conductor doesn't change in a minimal possible way. And then we can, so step 2 would be find G belong to ML of I, some power may appear here, ML gamma 1, with such that rho G, you can in fact find a new form, rho G is isomorphic to zeta 1 direct sum zeta 2. So once we have that, then rest is easy. So the way we have constructed G, what we notice that H, actually we have to remove certain Euler factors at certain set of primes. So let's call that set of primes I mean product of those primes IM, H, and GIM is congruent mod pi. That is first thing we notice. I'll describe what is M. But once we have this, then mu of F times F naught times GIM is actually congruent to. This essentially comes from the fact that on this coordinate, this is linear actually. So GH mod. So for every phi, let me write finite order character mod pi. We have this. Then and we know that the representation associated with this is that sum of two characters. So we could, in fact, somehow we should expect to relate it with mu of F naught Xi 1 pi, and there could be some twist Xi 2 pi, and then there would be some power of xp here, which I will not describe. Some maybe u, and so this is what we would like to do. However, as I said, there are some problematic set of primes, so we really need to remove those factors. So to do that purely for computational reasons, we actually need to look at a slightly different form. So what is F naught F tilde? This is just F naught applied on IM. Okay, so with this we can do, but however, there is one technical difficulty. The problem is that the entire construction of Hida, if you look at, there is one assumption. Actually, he does it for primitive forms, but what essentially he needs is this. So we look at the Hecke algebra correspond at that level. So gamma 1. So once we change it, it will have its level will change. Will be m squared. So it can be slightly smaller also, but let us write this, and then this is QP bar, and because this is an Euler form, so there will be a homomorphism. In fact, we can just look at K here. We can put K here, and it will work. So there will be a homomorphism like this, and assumption is that this splits. This is an algebra homomorphism. So in general, of course, if F naught is new, or you can already see that this level, even if it's slightly smaller, it may not be in general square free. So it's not very clear how this splitting will, when it will hold or it will not hold. But if F naught is not changing by applying IM, then already because it was new, it will split. Of course, we have examples, but we don't know when this F naught IM is not new, we don't really know when it will hold and it will not, although there are many examples for this. With this assumption, this holds. So there is theorem. Under this assumption, we can do this. Now, suppose then this side from here, if you apply F naught tilde times G IM is congruent to just characteristic ideal of, we'll have Selmer group of F twisted by xi1 and dual characteristic ideal of course this is applying some main conjecture for F twisted by xi1 and F twisted by xi1 and xi2. Then we have xi2. Both these over cyclotomic extension. I'll not write the entire thing. This is mod pi. Mod pi. And then using proposition 1, then this is equal to mod pi everything. This is proposition which I have erased. Proposition 1 implies this is maybe I'll just write xj sigma naught this is equal to, of course there will be xp here. Everywhere I am just missing, so there are twists everywhere. So as a consequence, we have LP J is congruent to this. We have done it after removing Euler factor, but at those Euler factor you can directly compare the you can directly show the congruences. Actually, there is a congruence for entire usual characteristic ideal xj mod pi. Mod pi. Yes. This is of course this we have been able to, we could do it only under this these technical assumptions. Although in some cases we can check that we can actually remove it, but this is not the best statement. We would like to remove this. I think it should be possible to do this. Yes. So as a corollary, we immediately have that corollary. If one of them, this or this, if LP is a unit, then or if one side divisibility hold, then it's 2. H. This is what we have at best as of now. I'll stop here. Maybe if you have some question, you can ask.
Thank you very much. So are there any comments or question or comments?
So I guess you are assuming the weight of F is larger than the weight of H, right?
Yes, yes. That
Yes.
I'm not sure if I stated in the beginning. So everywhere, this is. I stated in the beginning, but yeah, I'm not sure.
And you are assuming ordinarity for both.
Yes, that I have.
Yeah.
Said in the
But then, at least conjecturally, only the ordinarity for the F of larger weight is essential.
yes, that is
So,
what is
Yeah,
actually
which of
needed.
your part
In fact-
work can be
In
done
fact,
without ordinarity of the second one?
yes, in fact, the way we defined the Selmer group, it only we needed the filtration, the middle term was needed. So the filtration for H was not needed to define that. And this side, even this will work, everything, only because residual representation is reducible, and in computation somewhere we are using that. So one of these characters, J1, J2 we had, one of them is unramified at P. But yeah, that I think is not very essential. It should be, one should be able to do with only assuming that F is ordinary at P, entire thing.
The result on algebraic part at the beginning.
Yes, so that's
falls
where
with
there are
the-
some computations where we have used that the quotient is unramified. That we have used it, but it should be anyway. Residual representation is reducible in this case, so yeah, that's what in ordinary case we expect that. Yeah, in supersimilar. I mean, yes. So there are constructions. So we haven't yet looked at it. Those. It's the kind of simplest case we have looked at it yet, and yeah, there are more cases one can look at.
Any other question or comments? Okay, so if not, let's thank the speaker again.